10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And let's start. Welcome to today's webinar with the title Miniaturization, Function Reliability, Device Embedding PCB Sample WE.embed. I am Andreas Schilp, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is a qualified specialist from Würth Elektronik, Jürgen Wolf, Head of Advanced Solution Center at Würth Elektronik Circuit Board Technology. As usual, we now want to give you some information about the webinar and the webinar tool. You will be muted during the webinar. The chat function is switched off. You have the opportunity to ask us your questions at any time. I will show you how to do this in a minute. The duration of the technical presentation is approximately half an hour, followed by the question and answer session, which is exclusively available to the live participants. This will not be included in the video recording. We have compiled the most frequently asked questions about the organization and technology of the webinars in an FAQ section. See a link in the middle of this slide. So if you are new to this, the answers there might be helpful. After the end of the live session, we will ask you for your feedback in a survey. All previous webinars can be found on our Würth Elektronik YouTube channel and on our website, both for the technologies concerned and in the support section under Knowledge Video Center. And important note, we always get countless questions about this. The following presentation and the recording of the webinar will be available soon. You will receive the link via email next week. And this is new, next week already. As already mentioned, you can ask us questions. In your webinar panel, you will find the question box where you can enter your questions. Press the send button to send the question to us. Please understand if we do not answer your question immediately, for example, because it will be addressed later in the webinar. It will then be taken up in the final question and answer session. And we would now like to test this function briefly with you and ask you to tell us in the question field from where you are watching us and maybe how the weather looks like over there. So here in Künzelsau, we have really cloudy and rainy weather, so it's not nice at all. No snow, by the way. So in Belgium, it's also raining. So Almeria, Spain, 22 degrees C and sunny. Wow, jealous. Oldenburg, cloudy but no rain. Dublin, Ireland, blue sky. Oh, congratulations. Snow somewhere, maybe in the Netherlands, or is it in the UK, in Melbourne? So rainy in Holland, Sweden, and it's cold. So Netherlands also cloudy. So thank you very much for all your comments and welcome to the show. And again, we will be happy to make the following presentation and the recording of the webinar available to you in the proven manner. You will receive a link to it from us next week already by email. Okay, we are now ready for the webinar. I now hand over the screen to the speaker and start the recording with a new official welcome. Welcome to today's webinar with the title Miniaturization, Function Reliability, Device Embedding PCB Sample WE.embed. I am Andreas Schilp, your host of today's Würth Elektronik Circuit Board Technology webinar, and would like to welcome you. The speaker in today's webinar is a qualified specialist from Würth Elektronik, Jürgen Wolf, Head of Advanced Solution Center at Würth Elektronik Circuit Board Technology. Welcome back, Jürgen. And now I wish you lots of fun and new information.
Thank you, Andreas, for your kind introduction, and a warm welcome from my side as well to all you listening and watching today's webinar about our PCB sample WE.embed. So there is just a slide to introduce myself, and probably a lot of you have already heard or seen me, and we maybe have already been talking to each other. So just to sum it up here, a slide to give you my contact details and that you see who is giving you this webinar today. But let's move on to the agenda and our today's to-do list, to be honest. So what do you want to see today and what will I show you? I will show you about this PCB sample WE.embed. And to do this, I will first show you just a few slides about embedding of components or device embedding technology, some reasons why to embed components into the printed circuit board, and I will show you how it's actually been done. And then we will move on to the actual sample. I will explain to you what you will see and when you get the sample, and I will show you how to get the sample. During the marketing for this webinar, the ads for the webinar, there were already some of you trying to order these samples. Maybe some of you already got the samples. If you ordered a sample and did not yet get the sample, it will be sent out the next few days. So we have them on stock. We just need to send them out since there have quite been a few orders here for these samples. So yeah, why do customers of ours use embedding? And I just summed up a few of these reasons and the biggest ones of these reasons. And the first part is basically miniaturization. The second biggest reason is performance and function. And we have one part about reliability. When you look onto the miniaturization part, the first thing is, well, you can create your own package. What does it mean? Well, you can choose one of your own components or adding several components, make a system in package and create your own package here, as I said. So you do not need to have some kind of mold forms or whatever. You can just use PCB technology and create your own package of your own circuitry and use it on your main board, for example, and assemble it on your main board. The second part is, well, space saving of assembly area on the outer layers. So imagine you have a board and you already tried everything to downsize your components. You have already reached the smallest package of your components, but you still lack space on your outer layer. So the next step could be to go into the third dimension and move components to the inside of the PCB so that you can still get all the functionality you want to have in the geometry which is given by your application. The second part is, performance function. You can take components, put them inside of the board. You can surround them with copper and you can create an integrated shielding by usage of the copper from the PCB. Then we have the point you can get short signal paths because now you can think in the 3 dimensions. You can place components directly underneath other components and shorten signal paths here. For example, capacitors underneath active components or whatever you want to do. And you can protect yourself against plagiarism by hiding components inside of the board, by hiding them underneath components, by hiding them just away so that you do not see them in the first step. For sure, if you try really hard and, for example, do computer tomography or whatever, you will find those components. But the first step to do a rework of a board is to have a look on the board and to try to figure out the circuitry. And this is just much harder to do when not all the components are visible to the outside. And the last part is the protection against influences. For example, this could be mechanical impacts, this could be moisture or whatever. So you can hide and seal those components inside by burying them into the printed circuit board and having them surrounded with the epoxy compound and the epoxy resin from the printed circuit board. There is a secure and full surface fixing of those components. As I said again, for example, mechanical impact, those components are just secured inside the epoxy. And the last part is the thermal management. You can get the heat out of a component much faster by the usage of the copper in the PCB, for example, especially when you think of embedding a bare die, a power die, directly connected with copper microwires. You get a direct contact to the die and get the heat out of the system very fast. So thermal management is quite a huge part here for embedding of components. What's the status at Würth Elektronik? In our RT stands for Rot am See, here in Germany, in our RT plant, we have a full functional running process for all the technologies which we can offer. It's 3 different embedding technologies, and you will find them in our previous webinars, in our design guides, where I get a little bit more into detail how it's done for each technology. In our NH plant, which means Niedernhall plant, we have first series jobs as well in the technology where we soldered components on inner layers. And this is what I will show you now. So how is it actually being done? And I take basically the manufacturing process of our PCB sample to show you how components are being soldered onto an inner layer. So the first part, what we need to do is we need to manufacture an inner layer which needs to be assembled. And to do so, we basically, like any other inner layer, we are structuring the layout on this inner layer. So we manufacture the copper tracks here. What we do additionally now is that we have some kind of solder resist on this inner layer. And you see this on the right side, on a picture on the right side. We basically make small solder frames, solder windows surrounding the pads which need to be soldered. So not the whole inner layer is being covered with solder resist like it's being done on an outer layer. No, we just make small frames surrounding the pads to be soldered. And then we have a solder surface. This is a modified chemical tin, what we are using here. Modified, why modified? Well, basically we use it for 2 reasons. Reason 1 is, yeah, we need to have a surface which assists us in the soldering, so for the solder process. And the second reason, this modified chemical tin after the solder process helps us as an adhesion promoter for the subsequent multi-layer lamination. So we have 2 parts for this chemical tin, soldering and adhesion promoter. That's why we modified the chemical tin a little bit so that it can achieve both. Then we go to the assembly process. So we have a solder paste printing like in any other SMD process. We do the assembly on a standard SMD assembly line. And then we have one critical step, and this is cleaning. We need to 100% clean all the boards which will be used for the embedding. So all the manufacturing panels assembled with components run through a cleaning step, because we need to make sure that the surface of these panels is clean. There is no residue of any fluxes, etc. It needs to be clean so that nothing is being embedded inside of the board which is not supposed to be there. So we go to the multi-layer station, and we have prepared all the parts what we need. We have copper foils. Then we lay up a first layer of prepreg. We manufacture different other prepregs. You will see this later. We have prepregs with cutouts. We have maybe filling cores, special materials or whatever. But here in this case, we started with a copper foil. We have a fully covering prepreg. And then we take this assembled inner layer, which we have prepared before. And then we stack up all different kind of materials like prepregs, what you see here with cutouts. And in the bottom left picture, you see this, the prepreg is being cut out in the area where the components have been assembled. So we create like a first, we sometimes call it a virtual cavity. It's a real cavity during the layup. And later, when we go into the multi-layer lamination step, the prepreg, the resin in the prepreg starts to melt somehow, and with vacuum, pressure, and temperature, it flows inside of this cavity, and all the components inside of this cavity will be surrounded completely by epoxy resin in a void-free manner. Then we finalize this layout, so with different cores and the finalizing copper layer, we go to the lamination step, as I said, pressure, temperature, vacuum in the multi-layer press, and then the components are being surrounded with the epoxy resin, which comes out from these prepregs in this multi-layer stack up. The remaining manufacturing steps, well, basically are like any other PCB. So we can do drilling, we can do laser drilling, we go to the plating, we do the metallization of these holes, we structure the outer layers, we add solder resist, solder surface, we do the final contour routing or V-scoring, and in the end there will be a final inspection and a test. And this test you already might have heard of. Well, it's not a standard PCB test, so in all the projects which we do, we agreed with our customers what kind of tests are being done at the finalization of this PCB with embedded components. And this could be an in-circuit test, this could be a test fixture, a complete test stand. So it depends on what needs to be measured, it depends on the application, it depends on the board. We agree on what is being measured to finalize the PCB and send it out to you. So let's move on to the actual PCB sample, and I will show you what you will see when you get the sample in your hands. So first of all, I want to show you, you've already seen how it's been done, but this is the structure and then of this board. You get basically a board with 6 copper layers. There is an assembly on layer 4, and it's a top assembly, so the components are facing up. And the assembly is done by soldering. And in our nomenclature, this is basically written completely so that we know what's being done. So ET stands for Embedding Technology. So this is here, Embedding Technology. Then we see, okay, the total layer count is 6 layers for the overall board. It's a solder technology, so S stands for solder, M would be for microvia, and F for flip chip. If you want to know all the other technologies, just feel free to look up the past webinars where we explained all these technologies much more in detail and how it's being done. Then we have the internal component layer, so you see on which layer the components are being assembled, and we describe, is it a top or a bottom assembly on this layer, so that we always know exactly, due to the nomenclature, how would this stack up look like. This can be combined with all different other technologies. It can be an HDI, it can be a rigid flex or whatever, but the embedding part is defined here, that it says it's a 6-layer built-up. Soldering takes place on layer 4 in a top soldering kind of way. Then you will find a QR code. This is just so that you can have a quick access to our website, where we basically have the description and everything what you see here in the presentation, that you can have a look what is directly taking place in this part. Then you probably want to know what kind of components are embedded in this PCB sample. Well, this is an actual picture of the assembled inner layer, and you will find for each PCB 24 red LEDs, some resistors, some capacitors, a TVS diode, and 6 active components in different kind of packages. You will find UDFN packages, TSS OP, QFN package, and so on, just to show that different package heights, different package structures can be combined on the same layer to do the embedding for these applications. What I added here is the schematic of this PCB sample. It's an easy schematic. It's just a running light schematic. But why do I show you this schematic? Because on the bottom side of the sample, when you get it, you will find test points. So you can have a look into the schematic, you can run the PCB sample, and you can decide if you want to measure any test point and measure what you see here. I've added the description of the test points so that it matches with the schematic here in this picture. On the actual sample, you will just find the test points. There is no printing on the sample. As you see here, this is just for you to see and to match. And if you want to check, you can have a look into this presentation and see how is the schematic matching with these test points, and can do your measurement on your own do as you like. So what else do we have? We have an USB contact. And this USB contact is suitable for USB-A sockets, and it's just the power of the USB-A. So no data lanes are being contacted, so there is no additional circuitry that we like to, for example, if you think we want to have access to your computer, no, that's not it. It's just the power contacts of the USB-A. You can plug it in. And in between those contacts, you will find a depth milling to have a little bit better look onto the embedded components so that you see that there are actual components inside. And yeah, when you take the USB contact and you plug it in, you will see the light running through our logo. So all the LEDs inside are running through our logo. So the last question probably is, how can you get hold of this sample? Well, it's pretty easy. Either you contact your sales rep from your region, or you go to our website, go to the PCB technology portfolio. In the technology portfolio, when you scroll down, you find all our different technologies, and on the right side in the middle, you will find the embedding technology. And when you click on there, you get to the embedding page where you will find all the design guides, all the explanations, all the webinars, and so on. And there is a button for the PCB sample. You can click on there and order the sample directly from there. When you scroll down here, you will find all those descriptions which I have just shown as well. So you can either have a look into the webinar again, or you can go to the website and see what is inside and what is the sample about. So yeah, that's about it from my part. Thank you for listening, and I will hand over to Andreas again. He will show you what is being done after the webinar, and then we will move on to the question and answer session.
Yeah, thank you very much, Jürgen, for the detailed explanation about the device embedding technology, and especially about the sample, the physical PCB sample WE.embed. Before we get to our question and answer session, I now would like to draw your attention to our survey. The survey window will open automatically after the live session, and I would like to ask you to take your time to answer the 6 short questions. By answering the questions, you can contribute to making our webinars better and better. Here you can also make your suggestions or wishes for further webinar topics, and to be honest, there is a long list already. Finally, I would like to draw your attention to our next webinar. On Wednesday, the 6th of March, we will host a webinar on fast, faster, high speed Würth Elektronik physical PCB sample WE.speed. The webinar is of interest to PCB designers, developers, and students who want to dive into the world of innovative PCB technologies. So send us your questions in advance by email or ask them live in the webinar. You can already register for this. We are looking forward to meeting you. And now we look forward to your questions, which you can ask us directly via the question window. And we will also answer the questions that you have already asked during the lecture and have not yet been answered. So let's start with the first question, and this is, can Altium Designer handle embedded design?
Yes, Altium Designer is one of the EDA tools out there which can handle embedded designs. When you look into our webinar archive, you will find a past webinar where I actually did a live presentation using Altium to show how it's being done in Altium. There are some things you need to know there, some tips, some tricks, but it works basically very well using Altium Designer. There are a few other tools out there like Cadence Allegro in the miniaturization package, Suken ZR8000, Siemens Expedition, and Pulsonics, which are capable to do this as well. If you're not, or if you do not have access to to such tools, we just recently opened a design department here at Würth Elektronik. So even together with you, we could offer you the design that we implement for you when you create your circuitry. So just feel free, talk to us. We can show you how it's being done in the tools, or if there is no tool available for you, we could even take over the layout for you.
Okay, and especially regarding Altium Designer, there is a webinar we made in the past on our website, so you can feel free to have a look at the video recording there, so where Jürgen showed step by step how to do it in Altium Designer. Next question is, how thin can the final PCB thickness with embedded components be? Is 0.6 millimeter final thickness possible? And maybe also question about the thickness of the components which are possible.
Okay, so as you might probably already know, the thickness of the PCB with embedded components basically depends on the thickness of the components. The thinnest what we did so far was a PCB only 300 micron thick. There was an active bare die with a thickness of 100 microns being embedded inside. So it basically depends on the thickness of the components and on the way how this component is being contacted. The maximum thickness, what we can do, depends as well on the PCB now. We have a maximum of 3.2 millimeters of PCB thickness due to our manufacturing plants. So all the, for example, machines for solder resist and so on, they only can handle up to 3.2 millimeter, and that's the maximum in PCB thickness. And then you can calculate back what would be the maximum PCB, maximum component thickness based on 3.2 millimeters. So when you look on the solder technology, we need to have an inner layer core where we solder onto, and this needs to be packaged inside of this stack up. So somewhere between 2.6 and 2.8 millimeter would be the maximum component thickness possible for the embedding of SMD components, for example. We have one application running in the fab, to be honest, which is a little bit thicker, which is over 3.2 millimeter. But this is just because in this specific application, we do not have any outer layer structuring. This is just a pressing of FO4 and no copper or solder resist on the outer layers. And there we could go thicker because there we do not go through the machines anymore afterwards. And there the 3.2 millimeter is not a limit. But otherwise, if this is not the case, 3.2 millimeter, in that case, is the maximum PCB thickness. And the components always need to fit inside. So we cannot have any component protrude through the outer layers. It always needs to fit inside everything. And therefore, the components depend on this. And if you tell us my maximum PCB thickness, for example, needs to be 1.6 millimeter, together with you, we plan a stack up and we show you what could be the maximum component thickness. And if there is a component maybe thicker, then we just have to discuss if there is a way how to get around it, maybe have an alternative component, maybe there is a smaller package of this component, and so on and so on. But this will be discussed when we take a look on the BOM, the bill of materials, when we start or when we look on such a project.
Okay, so we have got a lot of other questions. Can you have two component layers? So I think this regards to the embedding layers.
Basically, yes. What we cannot do is we cannot take one core and make a front and a backside assembly, so no top-bottom assembly on the same core, because often due to this thickness limitations, which we have just talked about, we often take very thin cores, like 100 micron thick core, and assemble this core. And these 100 micron cores, they are basically very flexible. So we need to have a handling system, basically a carrier system for this thin core, and therefore we just can assemble one side of this inner layer core. But what we can do is we can basically assemble two different inner layer cores and put them into the same stack up, or even a third. But the question is just if it makes sense. But what we already do and did, that we take two inner layer cores, have them assembled with components, maybe even one on the top and the other on the bottom side so that the components face each other. It's just a matter of fact that you do have a real good 3D planning so that the components do not touch each other if they're on different cores. But other than that, yeah, we can do this. We can assemble 2 different layers inside, and that works, yes. And we do this actually in series production.
Okay, so regarding the areas covered by components and the complete PCB area, is there a maximum ratio component to PCB area which have to be regarded?
Yes, there is. You will find this in our design guide, and it's somewhere around 40% of occupation of the inner layer area, because the remaining area is still needed for getting enough resin out of the prepregs to flow into these, what I call virtual cavities inside.
Okay, so next question. Can you as well make plated connections directly to the pads of a die as part of HDI microwire plating?
Yes, we can do that. You will find this technology. We call it microwire embedding. When you look into our design guide, it's very well described in there, but we can do, if the component is in the right configuration, we can make microwires directly on the contact of the component, and yeah, that can be done.
Okay. Are there any limitation in the number of layers, both minimum and maximum? Will it be more layers if embedded solution is chosen compared to non-embedded? Okay.
So is there a limitation of layers? Yeah, for sure there is. But again, it's depending on the maximum PCB thickness. So if you would like to have 50 layers, we still need to have them into 3.2 millimeter, and I doubt that we get 50 layers inside. But 12 or 14 layer, that's not uncommon for such a build-up that we have this layer count. So we need to see what is your requirement, what is the component thicknesses, and so on, to see how many layers could be done. And do we need more layers due to embedding? Again, it depends a little bit. Could be, because those components need to have a fan out, a routing as well. So we have to see what the components decide, basically.
Okay, there are a lot of questions regarding capability for vacuum application, outgassing, ATEX, and things like that. Can you give a comment to that?
Well, yeah, outgassing, well, it depends on the material, what we use. The components basically are being embedded, and the outside world basically sees the PCB material. We have the measurements from our material vendors about outgassing, so feel free to contact us if you want to have those documents. A big part is always the solder resist. When it comes to outgassing, we are at the moment in discussion what we can do there. This is just a short outlook. Probably mid of the year we will have a separate, maybe not a webinar, but a separate newsletter about this, because we are at the moment checking our inkjet solder resists, what we are looking on. And it seems that there is a much better outgassing behavior of those inkjet solder resists compared to standard solder resist, due to the fact that there is no solvent inside of these inkjet solder resists compared to our standard solder resists, which need to be photostructured. And due to the fact that there is no solvent inside these inkjet resists, it looks at the moment in our research labs that those solder resists which have been applied by inkjet are much better in the outgassing department compared to standard solder resist. So yeah, mid of the year we will have more information. These are tests which are going on at the moment, but it looks really promising. And what was the second part of the question? It was outgassing and
so usage in high vacuum application. So it's more or less the same thing.
Yeah. So as I said, it depends on the material which we use to embed those components. And feel free to contact us afterwards, and then we will directly contact or discuss this based on the materials and go a little bit more into detail.
Okay, Jürgen, you already mentioned this in your presentation, but again, here the question, is this technology only available in rigid, or is it also combinable with flex, for example?
Well, it's basically combinable with all the technologies which we offer. So you can embed the components inside an HDI board. You can embed the components inside a rigid flex. What we do not yet have in series production is a pure flex, so that you take a polyimide or whatever and have a very, very, very thin component inside. We did this in public funded research projects, in German research projects and European, that we take very, very thin bare dies, 10 to 12 micron thick, and embedded them into foils. But this is not yet from the one side. The components are not in series production, those ultra thin components, and those build-ups in PCB part are not in series production as well. So this has already been looked at in research projects, but not in the series production due to the availability of the components. But other than that, for combining it with rigid flex, yes, that is possible. Combining it with HDI or whatever technology you want to have, it can be combined. We just need to find a way for the right stack up. And this is something we discuss in very early project discussions to find the right stack up. And other than that, just move on, do this. Yeah, it's possible.
Okay, now another interesting question. Do you have experience with embedding components with high frequency or radio frequency high speed materials, passive and or active parts?
This is actually just starting. So we are discussing the first projects, for example, to embed components into a Panasonic Mactron material. We did in the past some research about hybrid buildups, FR4, Rogers material, and radar dies up to 77 gig. And we could show that we have quite a lot of advantages by embedding those radar components inside, just due to the fact we compared it to the standard buildups where the components have been assembled on the outer layer and contacted by wire bonds. And just through the fact that we could get rid of these wire bonds, we have very low inductance buildups. Those loops from the wire bonds, they are basically minimized by a flat connection in the PCB. So yeah, we have a little bit of experience, and this is still ongoing work. Yes, so if you have an idea, if you want to check something out, again, just feel free to contact us and we will see what we can do.
Okay, so of course the question must arise, what is the cost difference between an embedded version and a traditional version? So I think the system cost in total.
Unfortunately, I cannot give you a precise figure or a precise percentage, like it costs 20% more, because there's a lot of points to think about. And when you look on the part, what adds to the cost, it's basically four points. So the first point is it's the basic PCB technology. So is it a rigid flex, it's an HDI and so on, this can be calculated. But then you need to take in account, we need to cut out materials so to create this virtual cavity. And this is a process which is basically depending on the amount and on the nature of the components. If there are more components, we need to cut out more. If the component is thicker, we need to cut out more materials or more sheets of prepreg. So it really depends on the BOM, basically. And this is where we come to the third bulletin, the BOM itself. So normally what we do is that we normally source the components, and this adds to the cost of the PCB as well. So it's not like a standard PCB where we just manufacture the PCB. We have now components inside and we have the assembly costs as well. That the assembly cost itself is basically due to the fact that it's being done on the standard SMD machines. It's basically, you can compare it with outer layer assembly cost. And the fourth bulletin, the fourth point is testing. We need to define which kind of tests can be done, which will be done. Is it in a circuit test? Do we need to have a test fixture? Do we need to have a complete test stand? What would be the initial costs and what would be the running costs? And those 4 points, they basically give you the overall cost of this PCB. And now you see, due to the fact that there are components being used, it's not that I can tell you it's 20% more, 15% more. It really depends on the build-up. It depends on the kind of components, the amount of components. If you want to have a ballpark price, just feel free to send us like maybe an idea of a board. We will have a look on the BOM and see what it is and try, based on the BOM, based on the PCB, try to give you a ballpark figure for your precise application. But I cannot tell you like it's 20% more or something like that. We really need to have a look onto the application, onto the BOM, onto the PCB, and then we can give you a figure.
Okay, regarding the costs, is it possible to tell about the costs for the PCB sample we have talked about?
I think
that's just one question of the participants.
I think the components were somewhere around €2 something, but the overall cost, actually, I never calculated it because it's a handout sample. I just checked if it's below what the German law needs to have when we send something out as a marketing gift. It's way below that, but the actual cost, no, I don't have it in mind, but it's below.
So it's less than €10.
It's definitely less than €10. Yes.
Okay.
As I said, the components itself is something €2 something or something like this.
Okay, so thanks. There's a question regarding the design guidelines. They could be found on our website in the embedding section, but of course we will send you this with email. Another question regarding the PCB sample. Have you used halogenated or halogen-free laminate for the PCB sample?
We only use halogen-free materials here. So yeah, it's halogen-free material. The only non-halogen-free materials or halogenated material which we are looking at the moment would be Mectron 6, but all the other materials which we are using are halogen-free.
Okay, to stay with Mectron 6, there's another question. Is it possible to fill cavities with Mectron 6 material?
This is an ongoing work at the moment that we check how good is the resin flow from Mectron 6. This is what I said earlier. This is in development, and this is something what we look at the moment.
Okay, so does that mean the complete stack up is done by Mectron 6, or is it just for the filling of the cavities? Just for me.
Again, it depends on the application, but mostly what we look at normally is full Mectron 6 build-ups. But maybe in future there could be some kind of hybrids. Yeah, we will see.
Okay. So the last question here is, if we embed components and add components on the top and bottom sides, the inner components will have to withstand 3 heat waves minimum. Is that a problem?
That's not a problem. The only thing what we have to look at is the soldering itself. We have an option. Sometimes the question occurs is what happens if the soldering or the assembly inside heats up too much so that we have a remelting of the solder paste inside. But we have an option of a higher melting solder paste, which has like a liquid temperature, something 20, 22 degrees above of a standard outer layer, lead-free, for example, SAC 305 solders. So this could be an option that we can look for if there is the need that the inner layer definitely 100% does not remelt, the inner layer solder paste. Yeah, we have to look on it if this is a requirement what you need, but normally we qualified everything inside so that you can still do some outer layer assembly as you do for a standard board. So double layer assembly and wave soldering, or yeah, that's what we qualified this technology for, to be honest.
Okay, so this was the last question from the audience. This brings us to the end of the webinar. We thank you for your active participation, and a big thank to you, Jürgen, for the detailed presentation and for answering the questions. If you have any further question in the course of time, please feel free to contact our speaker. The email addresses are shown here again. We wish you a nice day and a good time. Stay healthy and goodbye.